So, John and team, my name is Tanya Cole. I'm with Medtronic in the Knowledge Center. I'll be one of the moderators. I'm also joined by colleague Megan. She's also in here, and I think Shar is joining us as well. So there may be three of us moderating. We'll see, maybe jumping around a little bit. At any rate, for everybody else, you've joined Improved 3D Printing using the scientific method, and we're really encouraging engagement. So if you want to turn on your cameras, if you haven't already, I see some have, feel free to turn on your cameras, engage through chat, and even unmute and have conversations. So all of that is highly encouraged. And so John is presenting with two students, my understanding. So John, if you want to introduce who you also have in the room, and you can take it from here.
Okay, my name is John Peterson. I am mentor and coach from Team 2220, and I have been 3D printing for about 20 years now. I've come across various things, and I have with me today two of our mechanical leads. One of them is Brady, and the other one is Kai. So what I want to talk about today is a lot of people know how to 3D print, but it's not everybody has time to experiment, or they don't have the skills or equipment necessary to do it. And sometimes you're just going on a wing and a prayer as what you think the variables within 3D printing are going to do. So we're going to add more scientific data to that today using equipment that I'm used to using. I'm an automation engineer from 3M. And at 3M, we make a lot of web-based products and things like that. So doing tensile tests and things like that is second nature for us. We have a lot of equipment to help us with that. So let's get started. FDM will be our focus today, fused deposition modeling, or sometimes it's called fused filament fabrication. It's the most common one used by FIRST Robotics. There are other types that you might have, but as far as making workable, strong parts inexpensively, this is the best method to use. You can make things very quickly. It's pretty easy to understand. So we're going to go over some variables there. What we're not going to talk about are equipment, because that's different and changes all the time. And we're not going to talk about filament. Those are separate topics, very complicated in and of themselves. And filament is very interesting because the chemistry of this has changed so much, and it changes a lot every year. When I first started out like 20 years ago, we were using something called stereolithography, and the polymer used in there was extremely brittle. You could barely touch the prototypes and everything that we made. Whereas these days, something that comes out of our Stratasys printers are extremely strong. They get used in industry, bounce on the floor, hit with hammers. It's surprising what happens to them and they survive. But a lot of that comes from, I have a lot of experience and I know how to make and print these parts. And I'm hoping to impart that knowledge to you so you make a great robot with great 3D printed parts. Let's take a review here with a close-up of FDM technology. If you look on the upper left, you can see an extrusion device. It's sort of like squeezing toothpaste out of a toothpaste out, or a hot glue gun. In fact, that's how one of the guys who developed this process started working. He just layered up using a hot glue gun and made something that looked like this. And one thing you'll notice about it is it's not solid. The way this works is all the material that gets deposited down has to remelt and adhere to the next layer, but there's still gaps in it. So one of the first things you'll learn is that there are limitations to FDM, and it means that sometimes the best choice is to either machine a metal part or buy an injection molded part. And as an example, we'll get into that later too. But you can see how ideally when they join together, there's a little bit of overlap so that the machine with both this heat and pressure squeezes the layers together and holds them. The interesting thing about 3D printed parts made this way is that they're anisotropic. You can see the definition there. It means a substance having a physical property that has different value when measured in different directions. In this case, forces are acted on it. You can see in the bottom, we're asking to put in chat if you can think of another material that is anisotropic. It's a very common one, you probably use it all the time. You can see from the left diagram that shows the layers put together and the forces acting on them. Forces will eventually pull them apart cleanly somewhere where the layers were fused together. And on the right, you can see it's not straight across there or anything. It's jagged and broken. And what's happened there is the filament fibers themselves have been broken. And ideally, that's what you want, because the material is strongest in that direction by far. And that is something you can affect when you are slicing your part and laying it out on the build platform. And if any of you couldn't think of another material, very common one is wood. If you think of a 2x4, if you try to break it in the long direction, it's very strong, but you can jam a crowbar in the middle and you could pry the fibers apart. But before we even get into 3D printing, we're going to look at CAD related issues that you can apply to your 3D printed part to make it even stronger. A lot of you have probably made parts like this on the upper left-hand corner. You see how it's got a square inside and a square outside. And when the force is applied, as in the blue arrow, to this part, inevitably it's going to break exactly where it's shown in the red circle. So what you want to do is you always want to put a radius in there when you have a part like that, that has a force with a sharp inside corner. That smooths it out and makes it much stronger. And another thing that it does is whenever the machine has to come to a sharp corner, it has to slow down and actually stop. And what that does is it adds extra heat to that section of the 3D print and can cause it to warp later on. But what's really happening here, as you can see in this figure, the red lines are stress lines through there, flow lines, they call them. And you can see how they're on the left side, they're evenly distributed. And on the right side, they're evenly distributed and they're closer together because it's a smaller part of the part. But look at how close they come together at that square corner. You see how they're concentrated? So when you have concentrated stress, that's where it's going to break first. And you can see the lines of force are, again, separated and have some space between them when the fillet is added to the part. And it's a very simple thing. You just use a radius command and you add it right in there. If some of you are familiar with finite element analysis, it's a computer program that uses your CAD model and computes stresses on the part. And usually blue is low stress all the way up to red. And as you saw on the left where the flow lines are concentrated, high stress, computer has also predicted that's where you're going to have high stress. So get rid of those sharp inside corners. In these examples, you can see two parts. Sometimes those look like interlocking tabs or something like that. On the left is a poor design because it has a sharp corner, given the force from the green arrow. On the left is a better design. You can see they put radiuses and they put them on both sides, which is a good idea because the part will break where the arrow is in tension, but it can also be destroyed in compression on the other side. So that's why radii on both sides are important. The part on the bottom, again, just reflects a good design versus a bad design. And in this case, they've even decided that they'll need a bigger radius on the outsides. Maybe these tabs are squeezed together and it just gives them that much more strength. I mentioned finite element analysis before. In a lot of CAD programs, it is built into it, or sometimes it's just a plugin you can add to it. Expensive ones usually have it. And what they show you is, for instance, the part in the upper left-hand corner, if you want to model the stresses on it, you would do, for instance, you'd say that the backside of it is fixed, like it's glued to a wall. You apply a known force of a certain amount in that direction, and it will calculate stresses, as you can see in the red section. Those stresses would be in tension. But since there's a nice radius there, it's pretty well spread out. So that's a pretty well designed part. And if you look on the right, you can see a gear. Everybody's used to gears. Typically, the forces tends to be spread out, but in this particular part of the simulation, it's centered where the arrow is. And you can see where the high stress concentrations are. And so what you might do is, if you have the space, you got to make sure that the mating teeth don't cut into that area, but you might put a little extra radius on there, and then it would be good to go. It's especially important for plastic parts. Now, say you've designed this particular part. You started out, it was just 90-degree channel, just an angle iron. First thing you do to make this good is you'd add a fillet. It makes it strong on the inside. There might be a lot of force on this, so you'll add this little bracket here. It keeps the walls from collapsing. And you've decided you want to add a boss in here, and it's hollow, so you can thread it, put screws in there wherever you want. But just standing there, it's not going to be very strong. So you can add brackets to each side, and you can also stabilize it with the other wall with this bracket right there. All things that are quick and easy to do in CAD, but they make a huge difference when you've printed your part and put it into whatever application you're using it for. Of course, it also helps to know when you're designing your part, where are the forces going to be on this part, so you can reinforce them accordingly. All right, now let's look at some appearance related issues for nozzle and layer height size. You've probably seen a lot of these things with different machines. You can see on the left, they used a much bigger nozzle on the machine than they did on the right. The lines that they built it with are very visible. And on the right, ones on the left are probably more appropriate if you're making a functional part. The ones on the right are more appropriate if you are making an appearance related part, like this is. Also, when you're printing things that are thin and the angle on them is very long, you can run into situations like this. You can see on the very left, it's very coarse, the stepping there and everything like that. And then it gets finer and finer as it goes around clockwise. What you're looking at here is the one on the left has some much thicker layers. And as you can see, they bulge out along the angle and are very visible. On the right, you can see that because the layers are finer, there's not much that you can see. This is another kind of gross example of it. These three parts were printed 3 different ways. And you can see, depending on what you want, you might say, well, it's just a prototype functional part. I don't have much time. I'll go with the 9 minutes. Whereas the other one is, well, I've made all my final changes and everything like that. I have some fine features in there I want. So I'm going to do the one on the left. As you can see, much finer in layer height. But look at how much longer it takes to print that. That may be an issue. There's a lot of parts on robots tend to be quite large. And instead of 30 minutes, it could be 30 hours, literally. Here's a quick way to kind of calculate what it's going to be, even though your slicer will do it for you, but the print time is approximately 1 over the layer height. And if you think about it, that makes perfect sense. For instance, if you wanted to, say you're making a prototype this size, But probably want to use a larger nozzle if you have one, and larger layers as shown on the right. You can try it out, functionally, see what fits, see if you even like it. That only took an hour and 40 minutes. But when you finally have what you want to do, you might say, well, I'm going to use it in a finer case. I can survive waiting 11 hours and 16 minutes for my final product. There are other choices besides nozzle size and height, layer height, that affect time, failure resistance, and strength. Here is a big one. This is a classic example of what you want to change your shells for. And sometimes it's called shells, sometimes it's called profiles. There's any number of things that your software or your machine will refer to it as, but it's the same thing. In this case, it's see the outer layers there? And in machines that you tend to have in FIRST Robotics, if you set the shells or profiles to 6 passes or something like that, it's going to make them all the same way. But in this particular case, it makes a lot of sense. There's a spline drive on the inside of that gear, so that needs to be strong. And of course, the outer part, the teeth themselves, they'll be moving together, and by being thicker, they're stronger and they'll wear a lot more. If you look at the figures on the lower right, you can see 2 boxes, and they've set the shells to like 2 on the one on the left and maybe 6 on the one on the right. And what this gets you is the part is much stronger on the outside if it gets squeezed or something like that. And the inside, interestingly enough, it has the same number of shells on it. And what that's good for is especially if you're going to put a threaded screw in there, or even a machine bolt. Because if you put a machine bolt in there, you're probably putting that under compression, and you want to have all that force on all those layers, as opposed to the one on the left, where a lot of the force is going to be on the infill, and there isn't much there. And if you put threads on the one on the left, it'd probably chew right through the few shells that are there and just strip out very quickly. So again, it pays to know what is going through your parts, what forces are on them, whether you're going to have a bolt or threaded sections through them. But just keep that in mind. You've probably, if you've printed, you pulled this up, and it gives you a lot of defaults. 25 to 35% infill is pretty standard. I don't think I've ever seen anybody do 0%, and you do sometimes get 100%, depending on what characteristics you need, and we'll come across some examples of that later. Now, you know that in a part like this, the geometry of it, adding radii and things like that, is important. But to make it very strong, you also want to print it correctly, and you want to use your shells for your strength instead of your infill, because the shells, when you do that, all the fibers are either in tension or compression, and it's using the greatest strength that they have. On the left, you can see how they've done the correct number of shells so that it pretty much fills the inside. On this one, they don't have many shells at all, and infill takes over. And that infill isn't very strong at all compared to the fibers on the part on the left. There's a bigger example on the right. You can see how they've done a good job on B, using a certain number of shells in there. And you really have to look at this. You can step through in your slicer to see all the layers, and you can find anomalies in there because the machine, it's pretty smart, but not as smart as you think it is. Here's an example of, this is a professional level machine, and it has the ability to vary a lot of things, but even it came across some problems when slicing the CAD model. You see on the left, there's an upper part that sticks out, and it has that little fold in there. That little fold wasn't intended. There was some anomaly in the CAD model, just as the larger one on the lower part isn't even touching in some areas, just in one area. There was a CAD problem, and the slicer thought they were separate, and so this is what you end up with. By stepping through the layers, you're able to see that, and you can go back and correct it as shown in the right. You can see profiles in there are nicely continuous. Parts are all connected together. Here's another example of where you need to be careful about what's going on in your infill. Now imagine this part was had a shaft there that was driving the outside. What would probably happen very quickly is that shaft would strip out, because as you can see, there's a lot of plastic there. In fact, it looks like they attempted to have 100% infill, but the machine didn't do a very good job of connecting to the circular element in this part. It probably did what it was told to do, but the parameters weren't right. This is where, through experience and experimentation, you learn to use the advanced features of your slicer. And if that doesn't work, you may have to go back to even your CAD model and see if you can figure out what's going on. It's very important, as shown in the right. A lot of people do make plastic gears, or they make the hubs for belts. And as you can see, the one on the bottom, lots of infill gaps. That's not going to be very strong, is it? They've corrected it a little bit with some infill gaps. And then they did a little more work, and it's 100% fill there. That's very appropriate for a gear that's made out of plastic. In this particular case, we had some experience with this. This is the remains of a hub used to drive a rubber belt. It was wider than this. The bottom part pretty much remained intact on the left-hand figure, whereas the top part just stripped right out. There were two narrow belts on here, and they were driving off the same hub. One of them probably jammed and stripped it out. Now, if you look at this part on the right, you can see how there just isn't much infill in there. It's got nice shelling on the teeth, nice shelling on the drive shaft, but because the infill wasn't very good, you know, somebody probably accidentally went with just the standard 25 to 35%, and it just wasn't strong enough. It just stripped right out after it. I mean, it worked for a while, but then when it encountered some loads, it broke. And that's the last thing you want when you're going into a final match or something like that, is to have a piece just totally be destroyed. So keep that in mind when it's just, you need to follow the force, in this case, from the shaft out to the teeth. And if you come across an area where there isn't much material there, you'll know you need to make some corrections. In this case, strictly in slicing. You can see the infill there. There's hardly anything there. So let's get into some mechanics here, the strength and failure factors. Probably heard people talk about loads. There's different kinds of loads. Static loads, that's if you put down a bar and put a weight on it. You can calculate that. It's very easy. That's what most people use. But that's not really what happens with actual robots. Robots are running across the field. They run into field elements. They run into other robots. They run into walls. Happens all the time. It's a static load, but a dynamic load. They call it an impact load. Oops. That when the robot hits the wall. And you can see it's much bigger than the static load. It's usually a short-term force. You know, you hit the wall and you rebound. but all of a sudden you've calculated a part to hold 50 pounds, and all of a sudden, for a brief period of time, it encounters 100, 200, 400. You just, it depends on the speed and how much mass is behind it. So when you're calculating a load, you need to give it a safety factor, just like they do for bridges. Maybe a bridge will be 2.5%. You should make it much stronger than you've calculated, not just for impact loads, but because sometimes the way the printer makes it isn't ideal. So it's weaker than you think it is. In case you're wondering, the oscillating red line, a cyclic one, that's like vibration. That's what that's for. So how do we measure these forces? Well, this is what we do at 3M. We have a lot of these machines. They're tensile testers. This one's called an Instron. You can see on the left. And on the right, it's reduced to its basic component parts. You have things that grip the piece you're testing. Crosshead will move, and at the same as it moves, and that's measured by the computer. Computer also determines what load is being placed on the specimen. So let's see an example of an actual one in action here. There's no sound to this, in case you're wondering.
I don't think it's showing on the screen share.
It isn't? Don't you see it?
Not yet.
You might want to switch to a full desktop capture.
Tested this. All right. So what happens here, they take known size samples. I call them dog bones in a lot of cases. They tend to have rounded edges too, and they stretch them, and with known forces, they see how much they elongate, and then they see when they break. You can see the output of this machine as shown here. In the elastic strain section, that's like if you were able to do this, if you had a piece of metal, for instance, you can, to a certain range, you can stretch it, and if you let go of it, it goes back to its original size. Elastic deformation, that's called. But if you keep pulling on it, as you can see, the profile of the red line changes. It goes to what they call plastic deformation. That means that if you let go of it, it won't go back to its original size. And it's on its way to failure at that point. So what you want in a part is something that stays within this elastic deformation range. You want it to bend a little bit, absorb the forces of whatever is happening to it, whether it's hit from the side or there's a torsional force acting on it because it's some kind of a shaft. But then you want it to go back to its original size when the force on it is released. Otherwise, if you took too much force on it, it's just going to bend. It won't go back to the same place, and then it just doesn't work anymore. Here's an example here of what you might see on the machine. This is mostly used for materials like steel that are pretty strong. We'll get into what some different materials look like later. But it goes within its elastic range for a while, and then it starts to stretch. You see it goes up to its ultimate tensile strength. But at this point, it's beginning to be destroyed, and then it finally, because the force, you can see the curve goes down because the force required to deform it is less, and then it breaks. So these charts, and if you're going to mechanical engineering, you're going to go heavy into this, because this is really what defines all the materials you're going to be working with. And you need to know this so that you can place your material within the elastic range and you don't push it any further. So now the stress, that's the magnitude of the force shown by the green arrow. That's the force the machine puts on the sample. And it's force per unit area, pounds per square inch or whatever. And the resulting strain, as shown on the x-axis, that's how much the specimen will change. It's a kind of a ratio of the amount it changes from its beginning length. Stress is the cause. That's the force the machine puts on it. And strain is the effect. That's how far it deforms. And if you did a variety of stress strain curves, and it's possible some of the fibers that you purchase, they might have this much information from them. You can see, for instance, for the brittle plastic, which is what 3D printing used to be, you put stress on it, it doesn't move very far until it finally breaks. Not a good selection for a robot part, based on the fact that they're always running into things. The next one is more like the one that you want. When you put a lot of stress on it, it deforms for a while. You know, its strain increases, but it's fairly tough in that regard. And that's more the parts you want. Strong is one thing, but tough is an ability to absorb impact. And that's a great advantage to any part, because if you can absorb the impact, you're not likely to break. Now, a strain hardened part, that's usually metal. Sometimes it happens with plastic, but what that means is as you stretch the parts, they actually get stronger. You can see the curve starts to head up after a while. Now, an elastomer is related to plastics. Plastics are technically called polymers, but elastomers are like polymers in that they're long chain molecules, but they're also, the molecules are connected together at a lot more points, and you end up with something like a rubber band. You can pull it for a long ways and it just snaps back. You can see how in this case, they didn't put that much stress on it and it just deformed quite a bit. When you're looking at your filaments, you're going to see some of these things in here. And these are probably the most important. These are some common ones: ABS, nylon, PLA. Everybody probably uses a lot of PLA. And that chemistry, interestingly, has changed quite a bit over the years. And polycarbonate and some other stuff in here. And you can see how some of them are much stronger than others. And you have to determine if tensile strength is important to your part. And you have to design and lay it out accordingly. But if you look on the right, it's interesting how the part that's the strongest isn't the toughest. Nylon is used in a lot of things that require a lot of impact strength. You know, they make handles and things like that. You could make an X handle out of this. It's because it can take enormous forces on it and it's not going to break. But one more thing you might be thinking of, you need to take into account, is the temperature. If your parts are just hanging out in the air, you probably don't have to worry about this. But if you decide, oh, I've got a sim motor, I'm going to put it in a mount that wraps all the way around it, those motors get hot. You may find, though, for instance, that the PLA, maybe it doesn't melt, but it'll deflect and the motor will pop out. So these are pretty much the three material specifications you need to be thinking about. I've worked with some of the people at Underwriters Lab, big first sponsor, and they've been doing some experiments because there's fumes that come out from all of this. While this is a common industrial filament, ABS, it was their recommendation that students do not use this in their home or school environment because of the inhalation hazard of the fumes. There's plenty of other materials you can use, so please, given a choice, don't use ABS. Now, well, there's a lot of industrial equipment out there and companies working with this. What we don't have is somebody that knows ABS or knows 3D printing, and they're passionate about the materials behind it and everything like that. Well, here is one guy. Some of you may be familiar with him. His name is Stefan. He lives in Germany. He was a great 3D printing enthusiast. He spent a lot of time with it, and he got his mechanical engineering degree. So he's familiar with all the things we previously saw. He couldn't afford his own Instron. So what he did was he built his own. And you look at it and you think, well, you know, it's just made of big pieces of wood and plywood and stuff like that. But it matches the same, it has the same elements as an Instron does. And it's very stiff and strong. So for the small pieces he's working with, this is an excellent device. It even outputs the same curves, the same stress strain curves that you see from an Instron. So he knows how to do this. He knows how to analyze data. So I encourage you to go out, search for some of his videos on CNC Kitchen, and it's a good education in how to analyze data from mechanical elements. So here's how he's hooked up his machine. You can see there's the sample right there. It's got it in the middle, and it's interesting shape to it. And then he has, those are the grippers, and the machine applies a force in these two directions. It's basically pulling it apart. You can see it's in mid-cycle right there, and the bottom part is already deflecting a little bit. It's an interesting force he wants to apply here. It's along the axis, and it's a torsional force too. You remember back, we talked about how if the fibers are stacked, they're not nearly as strong as if you have a load that's along the axis of the fibers, as shown here. So he tested that. He wanted to know how important was that. You can see on the left how the samples were printed. You know, if you pull along that dressing, you're pulling the layers apart. He calls that a Z-axis sample. On the right, you can see he printed it flat. You look at the drawing, you can see that part is aligned along the axis of the fibers, so it's using their full tensile strength to make this a strong part. So let's see what he did. He did a first test here. Those are the XY hooks you can see in the upper corner. That's how they were laid out. And he made a change with, he tested out layer height here. Layer height here and the load on them. And you can see it doesn't vary a whole lot based on this. But if you look here, you can see when he pulled those apart, it just tore the fibers. And you should look at broken parts sometimes. You should do some failure analysis because it's very interesting. As I said before, the parts are torn along their axis and it uses the full tensile strength of the parts, and if you, or of the fibers. If you look down here, you can see how they're almost circular pieces. They're broken apart.
Hey, John.
Yeah.
Just wanted to break in just to give you heads up. We're about at five more minutes, so we're gonna need to take a break and then switch rooms.
Okay.
Thank you.
Sounds good. So anyway, you can see here the load he's put on that doesn't vary a whole by layer height, but let's go into testing these along the Z-axis where you're pulling the layers apart. You see how they broke cleanly. If they broke that clean, they probably didn't take much force to do it. And here's what he found. In testing this, you can see how the forces in the Z-axis where you're pulling the layer apart are much weaker than in the XY axis where you're breaking them along the fibers. So right there, that shows you it's almost 3 times as strong in that dimensions. So that's, if you remember one thing, remember that. Infill geometry. There's a lot of different types you can use here. All we're going to talk about right now is how much time these takes. I would suggest you using the rectilinear or the grid type here. It's very quick for the machine to do. If you ever watch it do some of these ones like the wiggle ones or the honeycombs, it takes it a lot longer. But then you may wonder, what about the strength for that? Well, it looks like the triangle ones have a little bit more strength, but is it worth to you? It's not that significant. And while some of these might be a little bit stronger, they take a lot more time to print. This particular chart kind of combines everything all together. So you can see the strongest parts, they tend to have triangular infill. And of course, you want to print those along the XY axis to get the strongest parts. Density, again, that's different from the infill type. He just used 2 here. He picked the strongest one from before, which was the honeycomb. And he's got the rectilinear, which was the fastest. And you can see where some of them are stronger. The honeycomb stronger at the lower ones, but if you get up above about 40%, this is around the standard here. And if you get above that, the rectilinear type is not only faster, but a little bit stronger in the parts. And of course, this one is your print time. You can see how, again, the rectilinear is much faster and the honeycomb takes a lot more. Shell thickness. One of the studies he did was he found out that making 6 perimeters is as strong as 2 perimeters with 100% infill. He hardly has any infill in there. So clearly, using perimeters, increasing those is the way to go to make a stronger part. And you can also make it lighter and you can produce it faster. This one just shows the weight on there, and the perimeter again is shown to be more important to make a strong part. Extrusion width, we're gonna have to wrap this up quickly. That's something else you can vary on your machine. You can see how it breaks cleanly on your standard ones and rough on the, when you increase the extrusion width, rough was usually associated with being stronger. And as you can see, 2 perimeters, 100% infill, or 100% layer height, and this one is 200%, and it's got 2 perimeters on there. Again, those are advanced machine settings that you should look into. And his conclusion about this was using wider extrusions seems to help layer adhesion because the layer is squished more into the previous layer. And you have to make sure you have the correct heat there too. And he's saying that's how, if you want a strong part, up the extrusion width, and that's almost directly in proportion to a gain in strength. So what important things have you taken away from the presentation today? If there's maybe just one thing, what do you think it might be? You can put that in the chat. Just got a few minutes here. Again, I'm going to go into the one that I think is the most important. And this relates to how you lay out your part in relation to the forces. If it's got a lot of force on it and you're pulling it apart in the Z-axis, it's not nearly going to be as strong as if the forces on it are ripping the fibers along their axis. There's other things, but if you remember one thing, remember that. So are there any questions that anybody has? You can unmute yourself and say them too. You don't have to put them in the chat. All right, well, if there's no questions, we're close to our end time, so.
We are, John, thank you very much. That was really informative. I learned quite a bit, and it's not even my area of expertise. So I think I'm hoping others had a lot to take away as well. And I believe that, yeah, the recording and the materials will be available. So
Yes.
if anybody wants to go back and consult any of the slides or refresh memory, that would be a possibility.
Okay,
Very good.
thank
Thank you.
you.